Thanks for braving the inclement weather to make it into class today. Today, obviously the first class since the midterm. We'll have the midterm back to you shortly, later this week. We're still grading it. And we get to kick off the second half of the course with one of my favorite topics, an area that is, of course, near and dear to my heart, which are metal-mediated alkene addition reactions, particularly those catalyzed by palladium, which have both synthetic and industrial, academic and industrial importance. And so we're going to begin with sort of general principles to think about the characteristics of metal alkene complexes and how those influence reactivity, and then we'll talk about the two different manifestations of nucleophilic addition to alkenes, both in an outer sphere process and inner sphere process, based on discussion of the Wacker oxidation and the Heck reaction. So to get started, I'll begin by introducing a set of rules to guide one's thinking about nucleophilic addition to unsaturated carbogenic groups bound to metals. And these are called Green, Davies, Mingo's rules. There's one familiar name there. Should be familiar, that of Malcolm Green. So these are rules that came out of Oxford. And they're really intended to help structure your thinking about relative reactivities of different unsaturated groups bound to metals. And so I'll just read through these rules, and then I'll show how they manifest themselves, and then really what we're focused on is today is this part of the rules. So first, nucleophilic attack is preferred on even number alkenes. So polyenes here on the short end ranging from ethylene to on the end, longer end ranging to complexes like hexatriene. And this, I think, is somewhat, so the second rule, I think, is somewhat intuitive, which is that the open form, the acyclic types of polyenes are more reactive than their closed forms. And then the third rule is that for even hapticity polyene ligands at a terminal, nucleophiles preferentially add to even hapticity polyene ligands at terminal position if the metal is highly electrophilic. Otherwise, they add at internal sites. So this helps you think about relative reactivity of the first two rules help you think about relative reactivity of different groups that might be coordinated to an 18-electron complex specifically. And then the third rule helps you have a general framework for thinking about site selectivity. And so combined, these rules manifest itself in this general order of reactivity. And I think the two that are probably going to be, I think the subtypes within this general workflow that you're going to see most commonly are additions to alkenes, addition to dienes, addition to al fragments. And so that's just a quick primer on those rules, and we'll have plenty of chances to work through those as we go through the problem today and the problem set. So now thinking specifically about metal alkene complexes and their reactivity, this is a little bit of review because we did discuss this earlier in the context of migratory insertion reactions. But there are two general mechanistic paradigms that we're going to discuss today. One is what we would call an outer sphere anti-type addition, and the other is an inner sphere migratory insertion type process. In either case, these reactions, they maintain the parent oxidation state of the metal, and there's a net flow of electrons onto the metal. So the metal, because it goes from having an alkene fragment to an alkyl fragment, is going to become more electron-rich during this process. I've drawn it here as in the outer sphere process, maintaining the same number of coordination centers, but then becoming anionic in charge. Of course, there's some variability depending on what other ligands are on the metal. And then in the case of the inner sphere process, I've drawn this as opening up a coordination site, but maintaining the same overall charge. And so in the context of palladium reactions specifically, you'll see nomenclature of Wacker type or Heck type used. And so a Heck type process is inherently inner sphere, and a Wacker type, as you'll see, Wacker type reactivity can actually be inner sphere or outer sphere. But when people use this nomenclature, they typically will use it to mean outer sphere when they're using it to denote mechanistic information. And so metal alkene complexes, like many of the different organometallic moieties that we've covered in class, have a spectrum of properties and reactivity. And so I've drawn the two extreme representations of a metal alkene complex here. On the left is the true metal alkene species, where there's relatively minimal back bonding. The metal here is electron poor, cationic. It would have ligand sets like CO, for example, and would be high valent nature. The other extreme is for low valent, electron-rich, anionic metals, where there's significant amount of back bonding, and thus the overall complex is best thought of as the metallocyclopropane. And so in terms of reactivity, here the alkene fragment is electrophilic, and in the metallocyclopropane case, the carbon atom is nucleophilic. On your midterm, you encountered this metallocyclopropane representation in the context of the Kalinkovich reaction, where it's ethylene is in complexation to low-valent titanium. That's a classical example of this mode of reactivity, and today we'll talk extensively about Wacker-type additions, which is a sort of canonical example of this left mode of reactivity. And I think one of the points that's important to note here is that remember that alkenes, their ground state are net nucleophilic in character. And so coordination of a pi-Lewis acidic transition metal results in an overall Umfelon process, where now that formerly electron-rich nucleophilic moiety now becomes electrophilic. I guess in this form, it's really just like enhancing the nucleophilicity of the alkene through back donation. And so when in doubt, you can ask yourself questions like, what is the oxidation state of the metal? Is it electron-rich? Is it electron-poor? Is it cationic? Is it anionic? Is it neutral? And that can help guide your thinking about which mode of reactivity to expect. Okay, any questions on these general principles? So now let's jump into the Wacker oxidation, Wacker type reactivity. I would direct everybody to this wonderful historical review, which I think for people interested in catalysis, particularly those who are working with palladium, this is really a must read. It's got an awesome blend of science and history, and really is a great really does a great job of taking you back to the era that a lot of these key discoveries were happening, and provide a historical context for that work. So, like many of the scientific or many of the catalysis breakthroughs that we've covered in class, the Wacker process was developed in Germany during. I guess this is now post-World War II, and Germany is rebuilding after the war. And also, one of the things that is interesting to note is that a lot of the companies that we've talked about, the German companies that we've encountered in class, these are geographically co-localized with some of the powerhouses of academic research at that time, like the MPI for Kohlenforschung, or then known as the Kaiser Wilhelm Institute of Kohlenforschung. So a lot of this was happening in this Essen, it's called the Ruhrgebiet, the Ruhr region of Germany, that is basically it's a big coal mining area. So they're big producers of hydrocarbon feedstocks, and thus this whole industry of processing hydrochemical feedstocks sprung up. And so the original Wacker-type reactivity was actually developed much, much earlier, so say 50 years earlier by Phillips. And it was found at the end of the 19th century that if you took palladium dichloride and allowed it to combine with alkenes, namely ethylene, in the presence of water, you would get out the corresponding carbonyl complex in the case of carbonyl compound in the case of ethylene, acetaldehyde, as well as palladium-0 precipitate. So this was actually used. Remember, analytical technology was not then what it is now. So this was actually used as an indicator for characterizing whether you had an alkene in your compound of interest. And so this mode of reactivity more or less sat dormant for the better part of half a century. And then a company called Wacker Chemie, for reasons that I'll discuss in just a minute, became interested in developing a commercially viable version of this reaction. Of course, the stoichiometric version is unlikely to be commercially viable because palladium is expensive, and if you cannot turn over the palladium that you're using, there's essentially no way to have a cost-effective process. And so after significant experimentation and optimization, both in terms of the catalysis, the underlying catalysis, as well as the engineering associated with this process, the Wacker Chemie and a team spearheaded by a man by the name of Walter Hafner in the 1950s was able to develop a commercially viable procedure for converting ethylene to acetaldehyde, where the overall reactivity here is this Phillips-type reactivity, but now palladium-0, which is generated at the end of the process, can be turned over through the use of a copper co-catalyst, which itself is then turned over by molecular oxygen. And so here's just a little bit more commentary on the context and motivation behind this key discovery. So this, the Wacker process was one of the first applications of homogeneous transitional catalysis on an industrial scale. We've discussed some of the other early processes here as well, like hydroformylation, hydrogenation, and the Wacker reaction, which were all sort of being developed within a 20-year window of each other. And so the underlying motivator here was that at the time in Germany and really worldwide, a lot of key industrial feedstocks were being prepared from acetylene. And so what kind of industrial feedstocks am I talking about? I'm talking about things like vinyl acetate, vinyl chloride, compounds that can have diverse reactivity and can be converted to a range of different products. And so acetylene, in turn, was ultimately sourced from calcium carbide. And the process to convert calcium carbide to acetylene is expensive because it takes a lot of energy. It's an energy-intensive process. And so at this time in the 1950s, there was interest in developing analogous processes with ethylene gas because it's cheaper, and adding some fuel to the proverbial fire was the fact that a new oil refining plant called by a company named Esso was opened right next door in Cologne. And so they had now very cheap access to ethylene, and they wanted to be able to convert it into all these key industrial feedstocks that are the building blocks of modern society at that time. And so the hypothetical reaction that was attempted was to convert ethylene to ethylene oxide. And I'll let you think about mechanistically what the idea here was. I'm not sure how deeply they thought about it themselves, but suffice to say they ran this reaction and they did not observe any ethylene oxide. And when they opened the reactor, they immediately smell that it was not what they expected, because this compound, if you've ever worked with it, has a very characteristic odor. So they smelled acetaldehyde, and then they were aware that they had gotten some interesting reactivity, but reactivity that was different than what they expected. And then there was a huge amount of process optimization that took place that I won't go through the details of. And so after a significant amount of development, they arrived at these sort of optimal conditions. And I'm going to highlight now a key point that I'll come back to again and again throughout today's lecture, which is that the mechanism of this very simple reaction is quite complex, and actually has been the subject of probably the better part of 75 years of debate in the literature. And I'll present to you what I think is the classical sort of textbook interpretation of the story as it stands now, but this is very much still evolving. And one of the central problems is that it's very hard to study. So it's known, I think, that when you change variables of the Wacker process or Wacker type reactions, that the outcomes change quite a bit. And so to study the mechanism, it's almost like Heisenberg's uncertainty principle. To study the mechanism of what's going on in this key nucleopalidation step, you need to somehow perturb the reaction. But by perturbing the reaction, you've changed it, and then you have this open question about whether you've perturbed it so far to be relevant to the key system, the real system, or not. Okay, so under the industrially relevant conditions, there's a relatively low chloride concentration, and this is the rate law here. You'll notice that in both the rate laws that I'm going to present, there's no water term, and likely in reality there is a water term in both of these rate laws, but because water is a solvent or co-solvent in these systems, it would be just reflected in the rate constant. It's very hard to meaningfully change the concentration of your solvent when it's one of your reactants. Okay, so here are the two rate expressions. The main difference is that under the industrially relevant conditions, you have negative second order in chloride concentration, and in the alternative conditions, which are high chloride concentration, you have negative first order, and then you also have a negative rate dependence on proton concentration in the industrially relevant conditions. And so essentially what this means, let me just quickly unpack this, is that you have positive rate order in palladium tetrachloride, this anionic form of that. So you know in your rate determining step, you have palladium. It needs to have lost 2 chloride anionic ligands. It needs to have coordinated a molecule of ethylene, and then it needs to have lost a proton. And so that would be consistent with a step that looks, let's say, like this. And then in these other conditions where you're at high chloride concentration, you have only negative first order. And so that would be consistent with a scenario that looks like this. So these rate expressions, these rate laws set the stage for the clear, the key mechanistic dichotomy, which is whether the water or hydroxyl group is attacking outer sphere in an anti-fashion or is reacting via migratory insertion via syn pathway. And so in either case, the resulting intermediate is the same, so these two pathways converge to a common intermediate, at least in the case of ethylene. And then downstream from this, we'd have some betahydride elimination process to make a palladium hydride, as well as the final product. Palladium hydrides you can think of in your mind as being essentially equivalent to palladium 0 species. They need to undergo a HX reductive elimination step, but essentially, these are already reduced forms of palladium. And so after that, then it needs to get reoxidized by copper. And so, as is hopefully evident from the rate laws, the overall rules that are normally taught in class are that at high chloride concentration, it's more likely to populate this state where you have 3 chlorides bound and there's not a vacant coordination site for the water or hydroxyl group to coordinate. And so high chloride concentrations favor anti, and low chloride concentrations favor syn. And so here are, I'll just show, as I said, there have been just a massive number of mechanistic experiments that have been done over the years. I'll present a couple, and then we'll use this as a springboard for problem of the day number 1. So if you want, while I'm writing this, you can look ahead to that. So one thing that's been done quite extensively are various isotope labeling experiments, deuterium and incorporation experiments. And so I'll provide two of the classical data points from Beckfall and Stille. So one of the challenges is that though this reaction, this alkene addition step, is in this case, or this case, each of these is stereospecific, then the stereochemical information becomes ablated in downstream steps. And so one of the ideas that's been actively pursued is, can you somehow trap the first label the substrate and then find ways to quickly trap the intermediates that are generated. And so in class we've learned that CO trapping is often fast, and so that's been attempted. And then from the NMR, you can read out what happened in the key nucleopalidation, the key alkene addition step. And this is work by John Stilley. And then another way to trap, so it's known that particularly at high chloride concentration, that one of the byproducts of the Wacker oxidation is after here, you can react with some copper chloride species to make the corresponding chlorohydrin. And so you can intentionally run the reaction in a way that favors chlorohydrin formation. Palladium to chloride process is believed to take place with inversion. This is from the Becklall laboratory. And then one of the challenges that often comes up and that I alluded to is that these are not necessarily industrially relevant conditions. In the former case, because of the addition of CO, which, as you might expect, could really perturb reaction outcomes. In the latter case, it's because of the reactions being deliberately run at high chloride concentration. Nevertheless, these results both establish the viability of this key anti-nucleopalidation process. Okay, so one of the questions that these experiments cannot readily address, but can be addressed based on the data presented in Pomelidae number 1, is how the betahydride elimination step takes place. So let's take a look at that. This shows two deuterium labeling / incorporation experiments. The first one using non-labeled ethylene plus labeled water, and the other using the opposite, labeled ethylene and non-labeled water. So take a minute or two, discuss with your neighbor, and then we will discuss as a class. Oh, thanks.
I think we established it elsewhere. Yeah, but I think in either case it would say successful. What's your sense? This way. This. It doesn't make sense. These are hemisphere. increase everything because if it just comprises angle, then we won't get whatever resurrection failure. So it's like very easy to transfer to yeah, it's
just like the
yes.
What about the
Oh, just goes the other way because you're running the other direction. So specifically just so if the just get like that sort of you'll see protein this would be a which I should just get sure about this. In this case, I just like this video. Oh, this material. Oh, because it's just going to be it's going to be related to the right. What time do you approach Wikipedia actually?
Okay, let's reconvene to discuss. Okay, Shuang, what did you interpret or conclude from these results?
I think that these two experiments indicate that both hydrogen and water lose perhaps as a form of hydrochloride during the cycle.
Okay.
And because one hydrogen from the alkene must be betahydride limited to the palladium complex, and then we incorporate into the complex
Okay.
to form that alkene.
So now you're talking about the right result on the right. So let's draw that out so everybody's on the same page. Okay, so you have this key intermediate, and from here, let's just say there are two possible pathways. One is that you could betahydride eliminate. To make an enol, which would then tautomerize to form and then let's say this is going to be D, but if I understood what you said, you're saying, Shuang, then you will get some scrambling at the alpha position. And in contrast, if you have a pathway where palladium reinserts, the palladium deuteride reinserts, then that could be a means of having a full label incorporation. Good. Anybody have anything different than that, or that builds on Shuang's model? So the key thing that this experiment allows you to probe is what happens post betahydride elimination. I think actually, and even at one point I was taught this and mislearned it or taught it the wrong way, that it formed some phenol intermediate, which then essentially undergoes dichomerization. But this experiment rules out that pathway and shows that after betahydride elimination or beta-deuteride elimination, the palladium hydride or deuteride stays bound to the alkene and can immediately reinsert. And this is actually a key theme. In some cases, if you have an electrophilic catalyst, the palladium hydride alkene intermediates that are formed from betahydride elimination can walk through stereocenters without epimerizing them, meaning that the metal hydride remains intimately bonded to a single face of the alkene throughout the catalytic or throughout the betahydride elimination reinsertion sequence. So this is a somewhat common thing that you should keep in mind. After betahydride elimination, there's one additional step that's not often drawn, which is that the betahydride has to leave, the palladium hydride has to leave, the alkene has to leave the coordination sphere of the palladium hydride intermediate that's generated. Very good. Any questions on that? Okay, so moving forward, I'll provide a little more, a little more information about what might be more relevant to the audience as synthetic chemists. So the Wacker process itself is specific to ethylene, and the conditions are optimized for ethylene to acetaldehyde conversion. Uses big titanium reactors. If in the lab you want to convert an alkene to a carbonyl compound, it's very unlikely that you want to run it in a reactor. And so various groups have contributed to useful, operationally convenient procedures that can be run on a laboratory scale. And so the Suji labs made important contributions in this area, and they identified a procedure protocol that it can be conveniently run on lab scale. And the key finding was the use of DMF as a co-solvent, which allows many different alpha olefins to participate in this chemistry. The regioselectivity is reliably Markovnikov selective under typical Suji-Wacker conditions. And that's because upon hydroxypalidation, this intermediate is formed where the metal is placed on the preferred terminal position. And then the other important factor is that upon metal complexation, you have partial positive charge buildup at the internal position, which is the position that's more likely, generally more capable of stabilizing positive charge. So this is both a steric and electronic argument. Of course, many groups have also been interested in being able to get the opposite selectivity outcome. And so I won't highlight all of the contributions here. The Engle lab has done important work on this topic as well. But I'll just highlight what I think is probably the state of the art at the present time, and I'll provide that reference in case anybody wants to try this in their synthesis. There's been at least one total synthesis in the past 2 years that has used this procedure. This is from the Grubbs group, published shortly before I started my postdoc. So the conditions here are a little complicated. And the mechanism is not very well understood. But essentially, every component is essential. It's not obvious what every component does. But one of the key thoughts or key mechanistic hypotheses is that, of course, we all know that radicals, in contrast to closed shell species, radicals tend to add to alkenes at the terminal position. And so it's possible that something like that is at play here. So this is straight out of the paper. If you don't like this model, don't blame me. But something like this could be a place where the nitrite is playing a non-innocent role. And that's something that's still studied. Part of the power of Wacker-type alkene activation is that it's not unique to oxygen-based nucleophiles, even though that's what's been most extensively studied. So I'll show a few examples here, and then we'll jump into problem of the day number 2. So I'll show CH nucleophiles or pronucleophiles, and then NH nucleophiles or pronucleophiles, and I'll give you a stoichiometric example and of each, and a catalytic example of each. So Suji in 1965 found that if you take this palladium cod bischloride complex and react it with sodium deprotonated form of dimethylmalonate, that you could get carbopalladation. And the cod here, the other alkene of cod here, essentially serves as a directing group of sorts, and it's able to lock palladium in this form and prevent betahydride elimination. A really interesting example, and if you're following the dates closely on this, you'll note that this predates essentially all of the work in cross-coupling. So it's a very important example of palladium mediating CC bond formation. And then for the catalytic example here, let's turn to problem of the day number 2. So we just saw this stoichiometric example from Suji, and it took the better part of 40 years for this process to be rendered catalytic in any way, shape, or form. And so Wiedenhofer, who we had out for a seminar a couple years ago, made a pioneering contribution in this area. He found that intramolecular CH pronucleophile cyclization to affect what's essentially like a Kanyine type transformation could be promoted by palladium. And so the mechanism is a little bit complex, but there are a couple of key questions. So one is this a syn or anti-pathway? And then the other is, how is the carbon-palladium to carbon-H conversion happening? And so if you think about the results of these two experiments, hopefully it will allow you to make a reasonable proposal. So think about that, discuss with your neighbor, and then we'll reconvene.
Oh, okay. I thought you were.
This is like the.
Yes.
Well, basically, so that's like what I mean is the double bond will be here or here, right?
So we can just assume there first, except the material.
Yeah, just swap over.
So that's why is this?
Why doesn't it go to that?
So why does it want to out? But I don't know how to split that.
That's exactly
And also, that's just that.
yeah, technically, no. Yeah, I guess so. But it doesn't do that because nothing requires. Well, actually, yeah. Another point is why well, I guess it's acidic or something like that. basically that.
So weird. If you go to the
Worst teacher ever. Like the mountain.
Okay, let's reconvene and discuss. I realize some people are still working, but let's get some discussion going. First, let's see if we can learn something from the first experiment. Zuchi, what do you think?
So first, palladium would pick up the deuterium on the substrate, and then the anion would form the Wacker type solution to form the alkyl palladium species, and then Betahydride elimination, followed by a series of chain walking steps to get to the alpha position on the left.
Okay. So let me see if I can capture what you are saying here. I want to draw this step out. Is this what you had in mind?
And this would correspond to the palladium oxygen species.
Okay. So the other, this is the C-bound enolate, and Zichi is saying should be the O-bound enolate. And then you had some D plus in solution. That's going to protonate here. Is that what you're thinking? Probably. Okay. And this deuterium you might expect to still be present, but remember that this position is very acidic. So to actually make this measurement, I didn't write this, but to make this measurement, this is after workup and column. So this CH bond we'd expect to be quite exchangeable. So that's just lost in the workup. But the key point is that if from here you had an immediate protonation step, then you would expect the proton to be here, and that's a non-exchangeable position. So that the fact that you don't get any deuterium incorporation at this position and do get some here is evidence that there's a chain walking process. Okay? Very good.
I'm curious.
Yeah.
Why would you chain walk to the left as opposed to the right?
Why would you
Oh,
chain?
like chain walk to the right to the 1, so the palladium is at the 1,4 Dicarbonyl position. I mean, the 1,3 Dicarbonyl position.
Instead of chain walking to the alpha position and then
Yeah.
getting deprotonated there? That's a good question.
Isn't that the answer to the second question? The second mechanistic experiment? Because you have sin, betahydride walk, and that hydride is.
Okay, sounds like Tucker volunteered for the second question. Okay, so what? Finish your thought.
So you should have anti-attack.
Okay.
Palladium binding, so as drawn, palladium binding on the bottom of that starting material olefin,
Okay.
and nucleophile adding on the top face
Okay.
to give the beta deuteron up, and then
So you wanted me to draw palladium on the bottom face. I'm probably going to make a real mess of this, so I'm just going to apologize right now, but I'll try my best. And so you want this to attack on the top face now. Is that right?
yes.
I'm making a mental note here to remember to make problems the day that I can draw more easily.
And then you have to have alpha between two ketones, that proton is also kind of up. Just think that's really
This one you're saying?
yeah, that one's up as well. Necessarily. And so then it can only betahydride eliminate on the bottom face of the ring if it's not dissociating. We'll then just walk to the left to put it going and be quenched.
Okay.
And the deuterons must stay on that face because the palladium's on the bottom.
Okay. Questions? Yeah.
For the top mechanism, so for that proton to exchange, or the deuteron to exchange, there's like deuteron and proton in solution. So why is it getting protonated by the deuteron?
Yeah, I didn't draw the level of enrichment, but let's just say it's not exactly 1 and there's some combination.
Oh,
And remember that this position is much less acidic, so on the workup, you're unlikely to exchange here, even though you're exchanging here.
but I guess the initial when it's initial.
So when you first generate the enolate, you only have D plus in solution. You should only have D plus in solution.
That deuterium comes from the palladium.
The deuterium
So
comes
the
from
palladium, when it walks, it kind of it's a palladium deuteride, right? So it carries that deuterium, or it just gets.
it should just
deuteride
go into solution as D, generic D plus.
Oh, so it's like a deuterium depolylation
Correct.
as opposed to.
Correct.
Okay.
Okay, any additional questions on that? Okay, very good. So that gives you a little bit of a flavor of carbon-based nucleophiles in Wacker-type chemistry. And there's also been significant progress with nitrogen-based nucleophiles. And so I'll show you a stoichiometric example here. Generic internal alkene plus generic dialkylamine, stoichiometric palladium allows the amino validation, and then these complexes can be processed further to get overall amino functionalization. And this contribution brings us to the chemist of the day. If anybody recognizes, you can shout out. Tanner's laughing because I mean you know. When my wife looked at the photo, she thought it was my dad. He actually looks a little bit like. Any guesses? Good. This is Bjorn Ackermark. The father of Swedish palladium chemistry, of which there's been a ton of activity. He spent most of his career at the KTH, that's the Royal Institute of Technology in Sweden, and is recently at Stockholm. Educated at KTH and at Stanford with Van Tamlin. Some of his famous trainees include Jan Beckfall and Lou Hegedus. He's still active, still has a research group at Stockholm. I realized I don't have his date of birth there. I didn't write that down. So one of the key findings of this study was that in the context of catalysis, it's very hard to use alkyl substituted amines with palladium because both the starting materials and the products, when they contain di- or trialkylamines, remember that the amine NH bond then can be a good sigma donor palladium. So you not only have starting material inhibition, but you can also have product inhibition. And so that's why these reactions work reasonably well stoichiometrically, and you can even draw this such that the amine can reach background and coordinate to palladium to make a four-member platecycle, but they don't work well catalytically. So fast forward several years, and people found that by deactivating the nitrogen nucleophile to make it actually less nucleophilic and thus less coordinated to palladium, reactions could be transformed to render catalytic. This includes work by Hegedus, Murahashi, and the example I've shown here is from Shannon Stoll's laboratory. And so often in this area of research, you'll see imide-type nucleophiles, amide nucleophiles, carbamates, some anilines work, but the key theme is that in all cases it's important to have a relatively less nucleophilic nitrogen nucleophile. Yeah, I didn't draw this very well. It's palladium acetate. Sorry. And then one of the emerging research areas in this topic that's very exciting, in my highly biased opinion, is thinking about ways to intercept the nucleopalette intermediates. One of the things that's different about nucleopalidation or migratory insertion compared to other elementary steps in catalysis is that it generates an extremely high amount of complexity in that step. It creates 2 new stereocenters, creates 2 new bonds, and so part of the inherent to the Wacker oxidation or the Heck reaction, which we'll cover in a minute, is that the stereochemical information gets ablated in the Betahydride elimination step. But if you can trap the intermediates, then you can really harness the full potential. And this has been most extensively studied intramolecularly. So I'll just show you a few examples of this. So classically, we know that Betahydride elimination can take place. No surprise there. We're just imagining this R group has some beta hydrogens here for the sake of illustration in case that's unclear. You can also trap these with strong oxidants. This should be no surprise for members of my group or members of the U group. This oxidizes a palladium-2 intermediate to a palladium-3 or 4 intermediate. We saw earlier that that CO insertion is rapid, can be rapid, and so that's a way to convert your carbon-palladium bond to a carboxylate group. And then we saw in the Wiedenhofer case that you can also intercept with a proton in a proto-dehalidation. And then this might make more sense after we cover the Wacker type chemistry. But if instead of palladium-2, you use palladium-0 and an aryl halide, then in situ you can generate a palladium-2 aryl species. And this can allow you to use palladium-2 aryls are sufficiently pyruvate acidic that they can still trigger this nucleophilic attack or migratory insertion, and that can allow one to achieve these carboamination transformations, carboetherifications, etc. And this has been work that's really pioneered by John Wolfe, University of Michigan. And let me just provide one reference. Becoming a little bit dated, but a really good starting point if anyone wants to read more about this. Chemrev from the Stoll group. So the power of Wacker type chemistry, at least in my opinion, is not just that it can convert ethylene to acetaldehyde, but that it's compatible with many different nucleophiles, and that if efficient trapping strategies are developed, it can allow one to connect with various third coupling partners as well. Okay, so I'm just going to quickly put up one more point on this, and then we'll talk about palladium-0 chemistry, or rather Heck chemistry. And this is really just in case anybody's needing to use Wacker type reactions. So internal alkenes historically have not worked very well. They're less reactive. So you saw when I drew the Suji-Wacker conditions. I drew it for specifically for internal. And so if one wants to do with terminal, you need to access cationic palladium. You can do that from this mixture of HbF4, EQ, DMA, acetonitrile. These are results from the Grubbs group. So this makes a bis cationic. Palladium 2. So this procedure might be interesting for some folks. And it's a modification of a procedure from Canada. Then so in addition to alkenes, it's perhaps not a surprise that these same principles can apply to alkynes. Take place with either syn or anti-selectivity. With dienes, and this will set up the next problem of the day. So if you want to look ahead to that, feel free. Dienes, these are typically anti. And then also allenes. Pial. Okay, based on what we've seen so far, let's see if we can have some insight on problem of the day number 3. So now instead of an alkene, we're going to consider a diene as our carbon electrophile. Palladium 2 conditions, benzoquinone as the terminal oxidant. So in Wacker type chemistry, copper, benzoquinone, air, O2, these are all common oxidants. And we have acetone, acetic acid as a solvent mixture, 2 different products observed in the presence and absence of lithium chloride. Why don't you take 1 minute to discuss it, and then we can discuss as a group.
basically fine.
Yeah, I think here's some chloride.
Okay, why don't we reconvene and discuss? Jess, what do you think? Okay, that's a good start. So let's coordinate to the diene. Okay. Okay. What do you think? Syn or anti? Okay. Good. So let's draw it as attacking from the back face. And the product of this is what? Is that what you have? Yes? What's that? Oh, is this what you meant for the intermediate? Okay. And then what's happening next? So palladium 2 pi owl, it's an electrophilic pi owl. If possible, I would like to react with a nucleophile in solution. Okay? And then now you have a decision to make. Let's take the top line first. With no lithium chloride present, do you think it's going to attack Syn or from the top face or the bottom face? Okay, so remember we said when we have chloride present, chloride is good at sitting in some of these open coordination sites and making it harder for an incoming nucleophile to pre-associate, right? We saw that in the Wacker case. So with chloride around, would you expect pre-association of acetate or attack to the backside? Attack from the backside, okay. And so the overall outcome here will be that these two groups are syn to one another. In these diene systems with palladium, they would normally go 1,4. And then in the absence of lithium chloride, now we're going to have an anti-product. And this is because actually, let me just draw this. It'll be easier. Acetate can engage in this kind of mechanism. Any questions on that? Anybody get anything different? So this is a good segue. Nucleophiles that are pre-associating. And so the other big category of palladium-mediated alkene addition are Heck-type pathways. And probably 95% of the time when you're talking about a Heck catalytic paradigm, you're going to be dealing with migratory insertion of a palladium aryl group into an alkene. There are some exceptions. There are alkyl Hecks that have been developed. There are aza Hecks. Aza Hecks that have been developed, but more often than not, this is what you're going to be dealing with. And so the big difference here is that it's like the syn form of the Wacker. You have syn addition of these two groups, and then now you need to have a CC bond rotation to make the CH group that you're going to Betahydride eliminate syn periplanar. And then the overall effect is that the two with an internal alkene, if you have two substituents here, there's in a Z configuration, they'll be trans to one another in the product. And so the early history of Heck-type chemistry was very much influenced by what was going on in the Wacker literature. And so people, based on the work from Tsuji, were thinking about what other carbon-type nucleophiles could be engaged. Fujiwara and Moritani reported a really interesting and timely example where they could take this palladium chloride styrene dimer. This is an early example both of Heck-type what then became known as Heck-type reactivity, and also of CH activation chemistry. In a stoichiometric sense that was then rendered catalytic. We found that aryl palladium intermediates generated from this cocktail, with a key point being acetic acid, which can facilitate a CMD-type CH activation. Allow access to these Stilbene-type products. And if you look at the date, you'll see that this predates a lot of the other important work in this area. So it's certainly a very meaningful contribution. And around the same time, Heck was focused on organomercury nucleophiles, and he found that treating, basically now we're running a Wacker type reaction, but we're using diphenyl mercury as our nucleophile, and this is going to transmetallate to palladium-2. So you'll see these conditions are very reminiscent of Wacker conditions. This was catalytic, using copper here to turn this over, also via the key palladium-2 aryl intermediate. This time by transmetallation. And one of the things that, in terms of the nomenclature, is a little confusing is that now we would refer to this type of catalytic cycle, as you can see in your handout, as an oxidative Heck type process. So the oxidative version of this reaction actually happened before the more classical aryl halide version. Oh, let me actually go over here for this. And then it took a couple years, and there were two key so I hope it's obvious from these two examples that how people were thinking about the polarity of these systems. That's really the key point I want to make, is that they were thinking inspired by the Wacker palladium-2 and some aryl nucleophile, whether it's an organometallic nucleophile or a CH nucleophile, electron-rich arene. That was the frame of thinking. And then Mizuroki in 1971 had a breakthrough paper where he switched the polarity, switching to low-valent palladium-0 and aryl iodide. So now the key aryl palladium-2 is going to be accessed via oxidative addition. And unfortunately, one of the sad parts of the story is that Mizuroki passed away at quite a young age, so he was never able to see the fruits of his labor. But this is a really seminal contribution, really undergirds all of subsequent advances in cross-coupling. Everyone's favorite journal, Bulletin of the Chemical Society of Japan. And the key finding, so he does use a palladium-2 precatalyst. One of the key observations was that palladium-0 precatalyst is also competent. Again, you're accessing this key organopalladium intermediate, this time via oxidative addition. And then the following year, Heck reported a variation of this. With the key change being now using organic base. Again, yeah. So now if you ever needed still bean, you had a lot of new ways to make still bean. I think this is probably Heck's most cited paper in his illustrious career. That work was done at Hercules Chemical Company, and Heck maintained an affiliation with the University of Delaware for quite some time. And so in terms of the nomenclature, what I prefer, and everybody might have their own preference, or their supervisors might have their own preference, but when I'm talking about the reaction, palladium-0 catalyzed, aryl halide, alkene coupling, I like to refer to that as the Mizuroki-Heck reaction, crediting both contributors. But when I'm talking about this mode of reactivity, I would refer to it as Heck-type reactivity. One, because it's shorter, and two, because Heck was an early contributor, arguably made the most important contribution in establishing the reactivity of palladium aryl species with alkenes. So it's a subtle point, but I think it is important as we write papers that we be scholarly. And so the whole catalytic, just in the interest of time, and that one of the two handouts that you received today show the catalytic cycle of the Mizuroki-Heck reaction. I'm just going to comment. I realize we're running a little bit long on time, so I'll make one comment on this. So basically, this just shows the sequence of events initiated by oxidative addition and then terminated by this HX reductive elimination that is driven by base. And if you look at the right-hand part of the cycle, you'll see this key step where an olefin needs to come in and bind. And so at this point, either an L-type ligand or an X-type ligand can be displaced. So either a phosphine, say, or a counter, like an acetate counter-anion, a halide counter-anion. And so there's mechanistic divergence there. It can either be a cationic pathway or a neutral pathway. Cationic pathways are favored when the coordinating anion is weak, like triflate. The ligands involved are bidentate. And the neutral pathway is favored most of the time with chloride, bromide, iodide, electrophiles, and with the common monodentate ligand sets. Those have important selectivity implications, as you'll see on one of the other slides, because neutral and cationic pathways give different regioselectivities with commonly used terminal alkenes. Okay, that's all I will say about these topics. We'll get to the last problem of the day at the beginning of next class, so you can think about that over the next 2 days. Probably, you might have already seen this example before. And I'd be happy to answer any questions after class. Thank you.